Great. Okay, so this workshop is on binary numbers and mensuration, and this is particularly covered in grade 10 and 11 as well. So what's our plan? For the next hour, we're going to look quickly at binary numbers and very simply converting between binary and decimal numbers. And then we'll look at mensuration, what it is, the unit conversions, units, and then conversions between them, and then, of course, surface area, volume, and the mid-ordinate rule. So binary numbers quickly. A decimal number is a base 10, like we use our fingers. I'm pretty sure that's where it came from. And we can break up any number. So 1, 2, 3, or 1,234 is broken up into 1,000 plus 200 plus 30 plus 4, which is the same as saying 1 times 10 to the 3 plus 2 times 10 to the 2 plus 3 times 10 to the 1 plus 4 times 10 to the 0. Now we can do the same thing with binary numbers, but a binary number has a base of 2, which means that each digit in the number is linked to a power of 2, and we only use 0 and 1 in our binary numbers. So basically like off and on, and this is used as the very basic programming for machines and for programming computers and so on. So if we have something like 1001, what we have is we count how many places there are. And of course, we start with, I'm pointing with my finger and you can't actually see that. Let me grab here. So here we go. So we've got 1001, right? So that's 4 numbers. So what that means is that we'll have 4 minus 1 is 3. And we count backwards from there. So we have 1 times 2 to the 3 plus 0 times 2 to the 2, because we're counting backwards, times 0 plus 0 times 2 to the 1, and then the last one is 1 times, sorry, that should be a 2 to the 0. Okay, now anything to the power of 0 is 1, so we have 1 times 8, is 8, and 0 plus 1 is 9. So 1001 is the same as writing 9. Cool. So how do we convert from a decimal to a binary number? And this is the long way around. I will show you a short method, which is quite handy. So we need to break down the number into base 2 numbers. So you need to know the various powers of 2, and this is why I created this table here. So it's very, very handy. All students should know at least up to 2 to the power of 9. In fact, even 2 to the power of 10, which is 1,024, which we just get by doubling 512. So if we want to convert 892 into a binary number, we know that 1,024 is too big. So we move to the next smallest number, which is 512. So we say 892 minus 512 leaves us with 380. Now we can subtract 256 from 380. So we do that and we get left with 124. Now 124 is smaller than 128. So we can't use the 2 to the 7. So that becomes a 0, right? And we move on to the next one, which is 64. So 124 minus 64 is 60. Now we can subtract 32 from 60. I'm going to go back to my laser pointer. So we have 28. We can subtract 16 from 28, which leaves us with 12. We can subtract 8 from 12, so we have 4. And we can subtract 4 from 4, which gives us 0. So we don't have any 2 and 1. So how I write that is we write, this is a 512 is a 1 because we could do it. 256 is a 1 because we could do it. 128 is a 0 or 2 to the 7 because we couldn't do it. 64 is a 1. 32 is a 1. 16 is a 1, 8 is a 1, 4 is a 1, and then 2 and 1 are 0 and 0. So if we take the first, we'll have 1, 1, sorry, 1, 1, 0, 1, 1, 1, 1, 1, 0, 0. And that's how you would convert from decimal to binary. Now, we can also go practice this. So shall we do it together? Let's do it together. Okay, I'm going to grab a oh, here we go. I've done the steps. So the first step is, but I do want to grab a pen quickly. So the first step here is to say 543, which is what we're converting, minus 512 is doable. So that's a 1. And we get an answer of 31, right? Now, we can't do 31 minus 256, so we write that as a 0. We can't subtract 128, so that's also a 0. We can't subtract 64, that's also a 0. And we can't subtract 32, so that's also a 0. So the next step is to say 31 minus 16, which gives us 15, so that is a 1. Now, 15 minus 8 we can do, gives us 7, so that's a 1. 7 minus 4 can do, so that's a 1, and we're left with 3. 3 minus 2 is a 1, so that's a 1 there. And we can say 1 minus 1 is 0, so that's a 1. So our binary number is 1, 0, 0, 0, 0, 1, 1, 1, 1, 1. Okay, so it's nice to use the table. It is quite helpful. This, of course, can be done on the calculator, but sometimes they lose their steps. So it's always good to write down what you're doing in order to get your binary number. So there it is in writing as well. Okay, now how do we convert from binary to decimal numbers? Again, we use our tables, but we write out our calculation using our 2 to the 9, 2 to the 8, and so on. So if we convert 1010101 to a decimal number, we've got how many places here? 1, 2, 3, 4, 5, 6, 7. So if we write from the back 1, 0, 1, 0, 1, 0, 1. So we see that we start at 2 to the 6. So it's going to be 1 times 2 to the 6 plus 0 times 2 to the 5 plus 1 times 2 to the 4 plus 0 times 2 to the 3 plus 1 times 2 to the 2 and 0 times 2 to the 1 and 1 times 2 to the 0. And then, of course, we write out these values. So it will be 64 plus 0 plus 16 plus 0 plus 4 plus 0 plus 1 gives us 85. Great. Any questions? Are we good so far? Just check. Great. Okay. So let's convert 111000111 into a decimal number. So again, we use our table, and let me get my pen again. So we get 1, 1, 1, 1. So we always work from the back. 0, 0, 0, 1, 1, 1. So what we've got is 1 times 2 to the 8, 1 plus 1 times 2 to the 7, plus 1 times 2 to the 6, and then we've got 0. So 0 times 2 to the 5, plus 0 times 2 to the 4, plus 0 times 2 to the 3, and then we've got plus 1 times 2 to the 2, plus 1 times 2 to the 1, plus 1 times 2 to the 0. And then, of course, we write down the actual numbers, so 256, plus 128, plus 64, plus 0, plus 0, plus 0, these ones here, and then plus 4, plus 2, plus 1 gives us a total of 455. So the shortcut is really awesome. Let me show you how to do it. So on our calculator, again, in normal mode, it's quite straightforward. If I have 478 and I want to convert that into a binary number, it's second function, and you'll see on the divide key in orange, there's an arrow binary. So I press the divide key, and that will give me the binary number. Now that I'm in binary notation, I can simply write my binary number into the calculator. So 11011. And to convert back to decimals, I say second function and equals, and it gives me a value of 27. So it's quite easy to convert between binary and decimal notation. Any questions? We're all happy? It's quite straightforward. It's a nice section. Okay, cool. So mensuration. Firstly, this is covered in grade 11 and grade 10. And of course, in grade 10, you look at converting units from normal standard units, square units, and of course, cube units. Now, we're units of measurement. So we're looking at kilometers, meters, centimeters, and millimeters. And we know that kilometers is 10 to the 3 meters. 1 meter is 10 to the 0. Centimeters is 10 to the minus 2, and millimeters is 10 to the minus 3. You can see this as a measurement of meters. We know that 1 centimeter is 10 millimeters. 1 meter is 100 centimeters or 1,000 millimeters. And 1 kilometer is 1,000 meters. So to go from a bigger unit to a smaller unit, we multiply, and to go from a smaller unit to a bigger unit, we divide. So if we wanted to convert between square units, we need to also square the initial conversion values. So if we wanted to convert 1 meter squared to measurement in millimeters squared, we know that 1 meter is 1,000 millimeters. And because our units are squared, we're going to square both sides. So 1 meter squared is actually 1 million millimeters squared. Again, for cube units, the same thing. We need to cube our initial conversion unit. So if we want to go from centimeters to meters, we are going from a small one to a big one. So we divide, and we divide by 100 centimeters cubed. So here we have 125,000 centimeters cubed divided by 1 million is our ratio. So it's 0,125 meters cubed. Right, let's work through surface area. So we've got the surface area of prisms, cylinders, pyramids, right cones, and the sphere, and this is all covered in grade 11. So the surface area measures the outside area of each surface of a shape. And we need to know the shapes with prisms, cylinders, pyramids, right cones, and spheres. So for a prism, we count the number of surfaces. Okay, and we note the base of the prism. So here you can see the base of this prism is a triangle. So our surface area would be 2 times the base of the prism plus the perimeter of that base times the height or the length of the prism. So here's an example. Calculate the surface area of the rectangular prism below. Our measurements are given in centimeters. So here, what we've got is 4,27. Okay, 4,15. So this is our base, which is a rectangle, and our height here is 6 centimeters. So the area of the perimeter is 2 times 4,27, and the base is 4,15 across. I've actually written these units in the wrong place. So we've got 16,84 as the perimeter around the base. Then the base area is 4,27 times 4,15. It's a rectangle. So we've got 17,7205 centimeters squared. So to get the surface area, we say 2 times 17,7205 centimeters. We use all the units for accuracy, and we round off on the last step. Plus 16,84 times the height, which is 6. So that is 35,441. And this is 101,04. So our surface area for this prism is 136.48. Okay. Now, the surface area of a cylinder is the base area, again, times 2, and then the circumference. So exactly like we did with the prism, except for we were now dealing with a circle, times its height. So our surface area is 2 times pi r squared for the area of the base, and then 2 pi r, which is the circumference, times the height. So here's an example. Calculate the surface area of a cylinder with a radius of 5 centimeters and a height of 20 centimeters. So our surface area is 2 times the circle area plus the circumference times height. So that gives us 2 pi r squared plus 2 pi r h. So here we'll substitute in. So it'll be 2 times pi. Our radius is 5 centimeters squared plus 2 pi times 5 times 20. This gives us 50 pi centimeters squared. This gives us 200 pi centimeters squared, or 250 pi centimeters squared. And then, of course, we actually do need to multiply out the pi. So that gives us 785.4 centimeters. Okay, the surface area of a pyramid. Again, it's the area of the base shape plus the area of all the triangular sides. Now, we only use regular shapes. In other words, all 4 sides of this pyramid are equal. Okay, if it was something else like a pentagon, then there would be 5 sides. If it was a triangular base, it would be 3 sides. So you do need to count the number of sides on the shape. So let's find the surface area of this square-based pyramid with sides 50 millimeters long and a height of 100 millimeters. So the first thing we need to do is to find the slant height h over here, and what that slant height gives us is a way to find the area of this triangle. So we place a point in the middle of A and B. Okay, and the midpoint of 50 millimeters is 25 millimeters, which is there. So we now know that this length here, GF, is 25 millimeters. Okay, so it's equidistant from any point with a square. So we can use Pythagoras. So we have 25 squared plus 100 squared. And that gives us 10,625. And if we take the root of that, our slant height is 25 times the square root of 17, or approximately 103,0776 millimeters. Okay, so from there, we now need to find the area of one triangle. So we know that the area of a triangle is half base times perpendicular height. The perpendicular height we calculated as 25 times the square root of 17. We know the base length of our entire triangle is 50 millimeters. So we have half times 50 times 25 times square root 17, which gives us an area of 2,576,94 millimeters squared. Now, the area of a square is quite straightforward. It's just length squared, which is 50 millimeters. So that gives us an area of 2,500 millimeters squared. That's the base. So we have to now give the surface area, and we do that by adding the area of base times how many triangles? 1, 2, 3, 4 sides. So 4 triangles times the area of the triangles. So we have 2,500 plus 4 times 2,576,94 millimeters. And that gives us a total of 12,807,76 millimeters squared. Cool. Any questions yet? Are we all still good? Great. Fantastic. Okay. So the surface area of a cone. The cone is made up of a sector. So if you cut out a cone and you spread it out on the table, you would actually see a sector. So we can find the area of the sector using the slant length of the cone and, of course, the radius of the cone. So the surface area of a cone is the sector area plus the circle area underneath. It's important to know where these formulas are coming from, because when you start doing composite shapes, you're going to have to start deleting parts of the surface area to make way for, say, the ice cream circle on top, which would be a sphere. So you wouldn't have that bottom area. You would just have the actual area of the cone, which would be pi rs. So it is a good idea to remind students to pay attention to all of that. Now, if you like my 3D shapes, these are actually made in GeoGebra, which are really cool. So I'll show you that just now if you want to take a look and see how to do it if we have time. I think we will have time. Okay. So the area, or the surface area of a cone, we can also write as pi r times s plus r. Sorry, I haven't had enough coffee today. Okay, so calculate the surface area of a cone with a radius of 1 meter squared and a height of 2 meters. Oh, sorry, a radius of 1 meter. So firstly, we need to calculate S, our slant height, and we do that by using Pythagoras. And you can see quite clearly there's a triangle here. So we have 1 meter squared plus 2 meters squared gives us 5 meters squared. So our slant height is the square root of 5. Then our surface area is pi times 1 meter, which is a radius, times our slant plus our radius, which is square root of 5 plus 1. And if we plug that into the calculator, we get 10,166 meters squared, and we round that off to 2 decimal places, is 10,17 meters squared. So we are just given the surface area formula of a sphere, which is 4 pi r squared. We don't need to go further than that. And so we just use that formula to find a surface area of a sphere. And that's, this question is asking us for a surface area of a sphere with a radius of 125 millimeters. So there we go. So all we do is substitute it into our formula. So it's 4 pi r squared. So it's 4 pi times 125 millimeters squared. And that broken down gives us 196,349,54 millimeters squared. And you can see I've done it here on the calculator. And you can see I've rounded off as well. This change button just changes the way the pi looks, so it multiplies the pi in once you are done with it. So how does changing the dimensions of a shape affect the surface area? Well, if we increase the length of the side, the surface area will also be increased. And if we decrease the length of the side, the surface area will also decrease. So by what factor does the surface area of a sphere with a radius of 2 meters increase when the radius is increased to 3 meters? So the surface area of the 2 meter sphere is 4 pi r squared, which is 4 pi times 2 squared, which gives us 16 pi. Here, the surface area of a 3 meter radius of a sphere gives us 4 pi r squared, and 3 squared is 9, so that gives us 36 pi. And if we create a ratio of 36 pi over 16 pi, because we're increasing, it gives us a ratio of 9 to 4, or 2 1/4 is the increase. And that's just by increasing it by 1 meter. So that's quite a substantial increase. All right, we are on to volume. Are there any questions on the surface area? Great, fantastic. So remember again, guys, if you have any questions, pop them into your chat and I'll take a look and answer them as we go. Okay, so what is volume? Volume measures the amount of space that a 3D object takes up. And this was discovered by, I can't remember who it was, some Greek guy who sat in a bath and watched as the level of the bath rose when he got in and then dropped when he got out. And he was actually tackling this problem of volume, and he couldn't come up with a solution until he decided to do something else. And that's why it's called the Eureka method, because he jumped out of the bath and shouted, Eureka. Also, the story goes. But it is nice to always hear the background for these sorts of things. So again, you need to know the different shapes that we covered in surface area. And so I'll go through each of these shapes with you now as well. Okay, so the volume of a prism. To find volume, we multiply the area of the base with the height of the prism, and this is applicable to all of the regular shaped sides of shapes, obviously excluding the cone and the cylinder, well, actually excluding the cone and the sphere. So if we want to find the volume of the prism given below, again, it's the same shape as we used for surface area. So our base area is 4,27 times 4,15. And yes, Lillian, how can I help you? What is your question? Can I let me find you quickly. There you go. Would you like to? Sorry, I didn't realize that you weren't allowed. Let me do it like this. There we go. Sorry, here I am thinking you can't ask me questions. Me that you don't want to ask me. Well, you can't actually ask. Lillian, did you have a question? You are, if you can just unmute yourself, then we can all hear your question. Can I unmute you?
Okay, how are you?
I'm good. How are you?
Hello.
Hi.
I'm good. I was unable to see the screen. I was only hearing your voice.
Oh dear. Are you sorted now? Lillian, can you see the screen now?
Yes, I can see the
Okay.
screen now.
Great. So we all sorted.
Yes.
Awesome. Okay, great. Fantastic. Okay.
Yes.
Let's go back to where we were then. Fantastic. Okay. So let's then right, so if we find the volume of the prism below, so again, it's the base area. So we're going to say 4.27 times 4.15. That gives us an area. Again, we use centimeters in this example. So it'll be 17,7205 centimeters squared. And then we multiply it by the height, which is 6. And so we get 106,323. In this case, I've used units cubed because we didn't actually give a measurement unit. Okay. If we want to calculate the volume of a cylinder, again, it's the area of the base or the area of the circle times the height of the cylinder. So here we have pi r squared times the h. So if we find the volume of a cylinder with a radius of 5 centimeters and a height of 20 centimeters, we have volume is equal to pi r squared times h. And we just substitute this into our equation. So it's pi times 5 squared times 20, which gives us 500 pi. And if we multiply those two together, we get 1,570,80 centimeters cubed. Right, so volume of a pyramid. Again, to find the volume of a pyramid, we multiply the area of the base by 1/3 and the height of the pyramid. Oh dear, I didn't put height in here. You will need to be able to find the area of the base shape. So whether it is a square or a triangle, a pentagon, you will need to know those formulas, which your students should know from grade 9 maths, but it's always good to revise with them. So here's an example. Find the volume of this square base pyramid with sides 50 millimeters and height 100 millimeters, which is the same question as we had earlier. So the area of the square, as we found earlier, was 2,500 millimeters squared, and our height is 100 millimeters. So we're going to have 1/3 times 2,500 times 100, and that will give us a volume of 83,333,33 millimeters cubed. The volume of a cone is the same formula as a pyramid, funnily enough. So you multiply the volume of the area of the base, which is a circle, by the cone's height and by 1/3. So the area of a circle is pi r squared. So the volume is 1/3 times pi r squared times the height of the cone. So here's our example. Find the volume of a cone with a radius of 1 meter and a height of 2 meters. So we have volume is 1/3 times pi r squared times height. So we have 1/3 times pi times our radius is 1 meter squared times 2 for our height. And that gives us 2/3 pi. And if we multiply that out, it gives us 2,09 meters cubed. Okay. The volume of a sphere. So the formula here is given to us as 4/3 pi r cubed. And we can simply substitute whatever value of the radius we are given into this. And this will give us 8,181,230 millimeters cubed. So that's a massive volume of tiny little millimeters. And this is 12,5 centimeters. So again, if we wanted to convert here in units, let's actually do it as an example. I just need to find my pen. So if we were converting from millimeters to centimeters, we would be dividing by 10, and then it's cubed, so it would be by 10 cubed. So we would be dividing by 1,000. So if we wanted to write this in centimeters cubed, we would have 8,181,23 centimeters cubed. Okay, so that is how that works. Okay, the mid-ordinate rule. Now, the mid-ordinate rule we cover in grade 11, and basically it is an introduction to integration. It's where the start of integration comes from. It's where the theory of integration actually comes from. So what we do is the mid-ordinate rule allows us to find the area of an irregular shape by dividing the shape into lots of rectangles with the same width. So you'll see I've just drawn this shape here, which is not quite as irregular. When they talk about irregular, they're talking more about a shape that has more bumps and like that sort of stuff. And sort of like woo and, you know, bumpy and not quite uniform and symmetrical. Okay, so we find the height of each rectangle by finding the midpoint between each of these coordinates. So the height is basically the average point between the two of these, and that's where the midpoint or the mid comes in our ordinates. The coordinates is the ordinate part, so that's why we call it the mid-ordinate rule. Okay, so this example is actually taken from the Sassel and Zalo book for grade 11, which I found online. I do have a copy of it, so if anyone would like a copy, please do let me know and I will share it as well when I email you the presentations as well. So a surveyor wants to determine the area of a piece of land. He takes perpendicular offsets at 10-meter intervals. So that he's telling you here that this is the dividing, or this is the standard division. And, you know, in our shape here, these would all be 10 meters wide. Okay. To an irregular boundary line. The ordinates measured at the midpoint are 10, 13, 17, 16, 19, 21, 20, and 18. Okay, so calculate the area enclosed by the mid-ordinate rule. And so this area here is, we'll have 10 meters times, and then we'll have 10 meters plus 13 meters plus 17 meters plus 16, sorry about that, meters plus 19 plus 21 plus 20 plus 18. Okay, and it's quite straightforward. We can just plug this all into the calculator. So we'll have 10 meters times, and I do it step by step because I just gonna put this here for now. So it's 10 plus 13 plus 17 plus 16 plus 19 plus 21 plus 20 plus 18, and that gives us 134. So we have 10 times 134 gives us 1,340 meters squared. So that's how we use the mid-ordinate rule to find the area of irregular shapes. Great. Are there any questions? I see this section finished much faster than I was expecting. So any questions, guys? Any thoughts? Okay. Great. So,
Mapula Lillian has a question.
yes.
Mapula.
Mapula, it was to do with your screen. Are you, Lillian, are you all sorted there? Okay. For those watching on YouTube, thanks for joining us. Take a look at our other technical math workshops available in this playlist. Okay, sorry guys, just to end off my recording.